This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 16, The Particle in the Box and the Real World, Section 16.1, The Particle in the Finite Depth Box. The wave function for the particle in a one-dimensional box with a finite depth must also satisfy the Schrodinger equation. H psi is equal to E psi. H is the Hamiltonian operator. Its physical meaning is the total energy of the particle. H is the sum of the kinetic energy operator and the potential energy operator. What's the potential energy of the particle? It's zero inside the box. And now we have a box with a finite depth. So let's say the potential energy is V0 outside the box. This V0 is a positive number. It's a finite energy barrier. Now inside the box, this is the Schrodinger equation because V is 0. We learned how to solve this equation. The solution is a linear combination of e to the power of ikx and e to the power of negative ikx. K is equal to the square root of 2me over h bar squared, and k times h bar is the magnitude of the momentum of the particle. Outside the box, we have a non-zero potential energy. It's V0. So we'll have to put this term in here. And then we move V0 to the right-hand side in here. And then we simplify this equation. We can see the second derivative of psi is equal to a constant times psi. Now let's look at a very interesting case. What if V0 is greater than E? This is interesting because when V0 is greater than E, that means the total energy of the particle is less than V0. The particle can never escape out of the box. If it did, the kinetic energy would be E minus V0. That's going to be negative. It's impossible to have negative kinetic energy in classical physics. It is possible, however, in quantum mechanics. Now let's look at this differential equation. How do we solve this differential equation? Well, if the second derivative of psi is equal to psi times a constant, naturally we think of exponential functions. So e to the power of plus minus kappa x are the solutions, where kappa is the square root of 2m times v0 minus e over here, everything inside the square root, and then divided by h bar. H bar is the reduced Planck constant. Now, again, E is smaller than V0. Therefore, this square root is a real number, and it's a positive number. So kappa is real, kappa is positive. To make sure the wave function is finite, we have the wave function to be a times e to the power of negative kappa times the absolute value of x. So now kappa is positive, the absolute value of x is positive. We ensure this wave function is finite. This wave function will never approach infinity. So again, this is the absolute value of x. This is the distance between the particle and the closest boundary of the box. All right. Now let me show you the shapes of the wave functions. This is the wave function with the lowest energy, second lowest energy, third, fourth, and fifth. If you recall the shapes of the wave functions for the particle in a one-dimensional box with an infinite energy barrier, they look almost exactly same, except that if you pay close attention over here, this wave function is non-zero outside the box. Over here, this is more apparent. This is non-zero. 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 Over here, you can see the value of the wave function outside the box is significant. This is comparable with the magnitude of the wave function inside the box. So what's going on? Well, this is the so-called tunneling effect. The wave function of the particle can be non-zero outside the box. That means the particle may appear outside the box. Again, the psi is non-zero outside the box. It can be positive, it can be negative. Therefore, the squared modulus of psi is positive. Therefore, the probability density of finding the particle outside the box is positive. Therefore, the probability of finding the particle outside the box is positive. Therefore, it's possible to find the particle outside the box, even though its kinetic energy is considered negative outside the box. Now let's look at the wave function again. It's a times e to the power of negative kappa x. Over here, this is the distance between the particle and the closest boundary of the box. So let's say the particle is right here. X is actually this. Okay, this is your x. All right. And then you can see if kappa is large. Again, this is kappa. If kappa is large, this exponential function decreases rapidly. Well, when kappa is large, that means, well, V0 minus E is large. So if the energy of the particle is much smaller than V0, that means this particle cannot appear really far away from the box. All right, it can still appear outside the box, but it's going to be very close to the box. The tunneling effect is minimal. However, when this E is very close to V0, all right, so V0 minus E is small, then kappa is small. When kappa is small, that means, well, the tunneling effect is significant. You can find the particle far away from the box. And now let's look at the mass. Look at the mass here. When the mass is large, kappa is large, the tunneling effect is small. When m is small, kappa is small. When kappa is small, this exponential function decreases slowly. That means you will observe more significant tunneling effect for much lighter particles. You will be able to observe the tunneling effect of electrons easily. For atoms, it's more difficult. And we never observe macroscopic objects tunneling through a wall. Now let's look at this kinetic energy again. The kinetic energy is E minus V0. Again, we are looking at the cases in which E is smaller than V0. Therefore, outside the box, the kinetic energy is negative. Again, this is called classically forbidden region over here and over here. And yet, the particle may appear in this classically forbidden regions. And now I'd recommend you to watch this really short video over here. Just control click.